Hello, and welcome to your Engineering Tomorrow Embedded Systems Lab intro. My name is James Venditto. I'm currently a PhD student in electrical engineering at Columbia University and a graduate of the University of Notre Dame, where I received my bachelor's in electrical engineering with a concentration in semiconductors and nanotechnology. As an engineer, I'm especially interested in optoelectronic and photonic devices, which are devices where either light produces electricity or electricity produces light, such as lasers, solar cells, or LEDs, just like those that you're going to see soon in our lab. Particularly, I eventually want to use these devices to address issues like renewable energy, think, say, solar power or energy efficient lighting, or sensors in cities, like detecting air pollution or gas leaks at their source. As for why I became an engineer, I was attracted to engineering from a young age, not just because I liked math and science, which I did, but also because I wanted to solve real problems involving real people. In high school, I found myself interested in a little bit of chemistry, a little bit of physics, and I wasn't really sure what exact major I wanted to pursue in college beyond engineering in general. So I decided to look into what I would actually study and what those job prospects would look like after graduation. In the process, I found electrical engineering, which is a really, really broad major. Electrical engineers do everything from the power grid, to computers, to lasers, to the very embedded systems that we're going to talk about today. So I didn't have to have my life figured out at 18 years old, which, as you can imagine, was a pretty big relief. One of the projects I'm actually most proud of happens to be an embedded systems project. When I was in undergrad, I spent a summer doing what's called an REU, a research experience for undergraduates at New York University. During that project, I worked with a lab called Sounds of New York City, who have been monitoring sound pollution at a local level here in New York for several years. This is really important because sound issues, construction noises, loud music, traffic, vary from street to street, which you might just realize from your home. And the best way actually to tell the city where problems or noise pollution are is to listen at a street level, locally. What this group does then is design embedded systems where noise sensors are hooked up to little computers called Raspberry Pis and are placed in the windows of people who live on that street. They then record records of when, where, and how loud unwanted or illegal noise outside is. This can then be given to the city so they know where noise pollution inspectors need to investigate. So for what I did, I actually helped design a setup for air pollution monitoring, where we replace those sound sensors with air pollution sensors instead to do basically the same thing, but now with particulate matter in the environment. I really enjoyed this project and I'm so proud of it because I was able to combine what I learned in school with something that affected my local community, kind of achieving that original goal of using math and science to solve real problems. So I hope I gave you a little bit of flavor of what an embedded system looks like and why we might care about them. But you're probably wondering, that's great, James, but what is an embedded system? You haven't told me that yet. And here's one answer, although I'm about to give you a few more in the coming slides as well. But in short, embedded systems can be thought of as a type of electronics where software, aka code, and hardware, also known as circuitry, work together to accomplish some task. Importantly, there needs to be some sort of intelligence, basically a computer of some sort, which the code can be written onto that can make decisions to interact with the environment and address those problems or do that task that we're trying to do. Because this intelligence is embedded or placed into the world, we call it an embedded system. At this point, I'm going to discuss a few more embedded systems terms, give you some more of those definitions that I kind of hinted at, before I get a bit into the nuts and bolts of electric circuits. And finally, I'll introduce you to your lab activity, where you'll be designing a virtual traffic light, which is one of the simplest but most important embedded systems out there. As always, all ET labs are created by a team of professional engineers and engineering students. In particular, I want to draw your attention to the mixed educational backgrounds of our team. This particular lab was developed by a mixture of electrical, mechanical, and computer science engineers. Engineering is a team sport and is incredibly interdisciplinary, which is a big thing to keep in mind. So, with that being said, let's get into some of those background basics I hinted at. The key to understanding embedded systems is understanding the idea of sensors and actuators. Sensors react to changes in the physical environment and produce an electrical signal that our embedded intelligence can interpret. Actuators, on the other hand, respond to an electrical signal from a circuit and perform a useful task, such as emitting light, heating up, or moving. Now that you have the definition, let's do a quick activity. Which of the objects pictured here are sensors or actuators? Can you guess? I'll give you a second. The LED, which we'll discuss more, is an actuator because it emits light. The switch, on the other hand, is a sensor because it detects position, whether it's being moved up or down, and affects the circuit accordingly. The fan is an actuator, which performs the action of spinning. And finally, the solar cell is technically a sensor because it reacts to light shining on it and puts current into the circuit. So we can also define an embedded system by the idea of sensors and actuators. That's great, but what does that mean? This next definition puts all that together. An embedded system is simply a combination of sensors and actuators that interact with the world to do something useful. Let's do another little quick exercise. Can you name any other examples of an embedded system? Here's a hint. You may have one in your pocket right now. So these are a few more examples. As you can see, they come in all shapes and sizes. Anything as simple as a thermostat to as complex as a robot in outer space is an example of an embedded system, so long as it fulfills the basic criteria that we set forth. You may be wondering what kind of engineers work with embedded systems as well. I want you to think back to what I said before about engineering in general. Do you remember? I said that engineering was a team sport. Living in an increasingly digital world, all kinds of engineers interact with embedded systems, particularly through sensors, but also actuators. However, there are several types of engineers that do specialize in making them, such as electrical engineers and computer engineers, because they have this specialized expertise in circuits and code. But embedded systems are going to play a big role in solving all of the challenges that humanity is currently facing. So I just want to give you a sense of how important these are and how ubiquitous. As you might have already guessed from our previous activity, they're all around you in your life. But there are certain engineers who specialize in working in embedded systems as a career field. Now that we have that solid understanding of the big picture, let's get into the building blocks of our systems, the circuits themselves. This is how the rest of this presentation is going to work. I'm going to walk you through basic circuit components and circuit equations and theories. Then I'm going to introduce several practice circuits so you can get a feel for how to build them and how they work together. And finally, I'll give you your traffic light mission and its specifications. So I've thrown the word circuit around, but how do we define a circuit? What is a circuit? Let's talk about electricity itself. If you recall from chemistry, every atom has electrons, which are tiny subatomic particles that carry a negative charge. In conductors, such as metals, they can move when we apply an electric field, which pushes them in one direction, and they begin to flow. Once they flow, they carry energy in that direction. This flow of charge is what we call current. At its heart, a circuit is simply a complete path for current to flow. At a minimum, we need a source that provides the energy and an electric field, and a path that returns the current back to that source. A complete path or circuit, if you think of like a racetrack. In this case, we have a very basic circuit meant to turn a light bulb on and off. The battery in this circuit is the energy source and the place that electrons flow to and from. The switch, which remember is a sensor, opens and closes the circuit, which determines whether current flows or not, and of course determines whether the light bulb should light or not. Because the current needs a complete path to reach the other terminal of the battery, opening the switch will prevent current from flowing in the first place, which means the battery can't light up anymore because no energy is being delivered to it. However, when I close the switch, I complete the circuit, the electrons can flow all the way from the positive terminal back to the negative, and energy can be delivered to that light bulb. So how do I describe this mathematically? That was a nice little description, but we need to do just a little bit of math to get a better understanding of what's going on. There's one equation above all others in circuit theory, and that is Ohm's Law. It's as important to circuits as Newton's laws are to moving objects. So V equals IR. This equation relates voltage, current, and resistance for any component in any circuit. V is volts, which is measured in volts, voltage. R is resistance measured in ohms. This little symbol here is actually ohms. And finally, current, which we just talked about, I, is measured in amps. So voltage is related to the electric field I mentioned earlier, and it comes from that source of what's moving the electrons. It's a little difficult to explain, but you can sort of think of it like a form of potential energy. Current, which we discussed, is the flow of charge. And finally, resistance, this new term I'm throwing at you, is the difficulty that current has flowing. If you think of it kind of like water flowing through a pipe, your resistance is how wide that pipe is, and your current is how much water is flowing through it. The voltage can be thought of sort of like gravity. If I take a pipe and I have water flowing through it, and I tilt it up a little bit, water will flow more easily, right? Because gravity is helping it out. That tilt can be thought of like voltage. The flow is current, and how wide the pipe is or isn't is resistance. If I make the pipe wider, I reduce the resistance and more water can flow. Electricity works very similarly. And you can see, if you look at the equations, that as resistance increases, the total current flowing will decrease if you don't change the voltage, such as if I have a battery with the same voltage, the same as our water analogy. Also, if there's no voltage at all, it's just kind of like if my pipe was laying flat and there's no gravity helping me out, nothing's going to happen to the water. The same thing. If there's no voltage in my circuit, say I remove the battery, there's no current flowing, and nothing interesting will happen in my circuit. So that was a lot of information. If any of this seems overwhelming, don't worry. Your practice workbook does have a lot of examples that will walk you through this in more detail. I just want to give you a big picture idea of what's going on in your circuits. You also may have noticed at this point too that we didn't actually give you any physical circuit components to build with. And that's because we're going to be constructing our circuits in an online program called Tinkercad today, which allows us to simulate the circuits and do all the coding in one convenient little place. At this point, I'm going to introduce you to what some of these circuit components that we work with look like in Tinkercad, and then explain a little bit about how to do the wiring. Here are the components that all of your circuits are going to start with. The Arduino Uno, which is the embedded intelligence that I mentioned earlier. It's also sometimes called a microcontroller, and what that is essentially a small computer with memory and programmable input and output pins. And what input and output pins are simply places where I can turn the voltage on or off, and that's controlled by code. So imagine a battery where I can unplug it and plug it back in, and that action is controlled solely by a line of code. Next, we have a breadboard, and this is a series of metal rails arranged in rows and columns that allow you to connect circuit elements without having to solder or fuse them together. This is sort of where everything else happens. We put our other circuit components on the breadboard in specific places to connect one element to another. You can think of it kind of like a wire, but without actually having to physically take a wire and push things together. It makes our life a lot easier, as you'll see when I demonstrate Tinkercad. Resistors are similar to wires, but they importantly add resistance to our circuit. So you may be confused because I just spoke of resistance as if it was a bad thing. Like resistance stops current from flowing, so why would I want to do this? As we're going to see in a minute, it's actually really important to add resistance into a circuit because it reduces the amount of current, which can be a bad thing in some circumstances, such as what we call short circuits. And finally, the star of the show is the LED, or light emitting diode. These are a particular type of actuator that glow in a certain color when current flows from one leg to the next. They're very similar to light bulbs. The important difference is that current only flows in one direction. And you may notice on the picture here that it says positive leg and negative leg, and that the two legs don't look exactly the same. That's because current has to go into the positive and out of the negative. If I put my LED in the reverse direction in my circuit, it won't work properly. And that's a fundamental principle of the semiconductor material that it's made out of. But it's important, I'll show you in a little second, that you need to put them in your circuits correct for that very reason. So speaking about the flow of current, there's also a few things to note about how the breadboard connects elements. They can be a little tricky to use, so I want to make sure you understand how the current flows in them. To start with, these power rails on the edges, which are these colored rows labeled with a red plus and a blue minus, are what you'll be using to connect back to the Arduino itself. They just look like the terminals of a battery, so you can think about them the same way. For these rails, the connections are vertical along these lines. So if I plug a circuit element, like a resistor or an LED, into one of those holes, and then connect it to another hole on the same rail, it's connected. So I can put a resistor in one hole and an LED in the next on the positive rail, and they're both connected to the positive terminal of my battery. But if I use these horizontal rows, you'll see that the connections are horizontal, not vertical. So you actually have to base your connections off of the numbers and not the letters. You'll also notice that they don't go through the middle through that kind of gap that you can see. For example, E does not connect to F. And again, this will make more sense when I demonstrate in Tinkercad. If you think about, just as a quick example, 1A connecting to 2A, they don't connect. But 1A is connected to 1C, and so on and so forth. You can see how if we put one of the legs of a circuit element into these rows, we can effectively connect them as part of our circuit, and current will flow along that row to get from, say, a resistor to an LED, and eventually back to the battery. Now, I also mentioned short circuits and why we actually want to use resistors, right? So let's think about Ohm's Law again. Let's say I have a constant voltage in my circuit, like a 9-volt battery. What happens if I decrease the resistance so that it's very, very small? What happens to the current? I'll give you a second to think about it. When the resistance approaches 0, the current must inversely get really, really large. This creates what we call a short circuit, which is where current goes right back to your source without traveling through any meaningful resistance. In real life, this can burn out your battery because of the amount of power that it has to output. This can also damage your devices, so if you have an LED, it might burn out, and in the worst case scenarios, this is how fires are started. Now, luckily, you're not going to have to worry about any fires in Tinkercad, but you still want to keep this design principle in mind because Tinkercad will record if you have a short circuit, and you'll see this little explosion symbol on your LED. That means your LED burnt out. So you don't want to burn out your LEDs. So you still want to use resistors in Tinkercad. And when you're thinking about the fact that we're engineering for a real traffic light, if I'm simulating it in Tinkercad, I don't want my traffic light in real life when I build it to break because I forgot to include a resistor. So we want you to include them as well. And to avoid them, we're going to have to pick the size of the resistor appropriately so that we have enough current to light the LED, but not too much to make it burn out. At this point, I'm going to demonstrate the basics of how to set up Tinkercad and how to build our first example circuit, which is just a glowing LED. Welcome to Tinkercad. This is the home page that you'll land on when you first log into Tinkercad. So when you go to tinkercad.com, you can create an account using your school Gmail address. You don't actually have to create an account or password. Using Gmail will allow you to log in straight away and get to building. This is the dashboard page. So you'll notice here there are a few sections, 3D designs. If you've done our 3D printing labs before, this may look familiar to you. But today we care about the circuit section. So we want to scroll down and we want to click on circuits. This will bring us to our designs. You can see I built some circuits before. They're already here, but we want to start from scratch. So we'll click on new and we want to click on circuit. It'll load for a second and it will bring us to our circuit building area. So you'll notice a few things to start off. On the right, we have this drop-down menu of circuit components. We can see the resistor, the LED, our Arduino, and our breadboard. This is where we'll get all the circuit elements that we'll be working with today. You'll also notice a code tab. I'll get to that in a little bit. And start simulation, which is how you'll plug in your circuit and make it start working. But to begin with, I need an Arduino and a breadboard to be able to do anything interesting. So I'm going to grab the breadboard by clicking on it. I'll click again and place it. You can name it, but I'm not going to do that today. If I wanted to delete something, I can click on the garbage can to get rid of it, but I want to place it. So I'm going to place it, and you can also rotate it, which can be very useful just so that it looks more like the pictures in your student workbook. Zooming in, I want to draw your attention to what I was talking about before, and perhaps this will make it a little bit clearer. The way that we connect things in the breadboard. The different rows that are connected are actually highlighted. So you can see if I focus over the plus voltage rail, everything here is highlighted, meaning that all of these little circuits are connected to one another. And the red square is just where I would place a wire. If I go to the horizontal rows, you'll notice that these 5 across are connected, but they're not connected to these 5. They're separate. So if I wanted to connect something from row 1, A through E, to row 1, F through J, I'd have to connect a wire across, and now they would be connected. But on their own, they are not. The next thing I want to do is to place the Arduino itself. I can place that here, rotate it so it looks more like the pictures, and bring it in line. You can notice here that we have several pins, such as a 5-volt pin, which can be thought of like a 5-volt battery, and ground. We've been talking about the positive and negative terminals of the battery, but at this point, you can think of that 5-volt pin as the positive terminal of a 5-volt battery, and ground, GND, as the negative terminal of your 5-volt battery. So anytime that we want to connect negative, think ground. These on the right are the digital pins that I also mentioned before. These are the little areas where we can turn the voltage on or off, and when I demonstrate a blinking circuit in a little while, you'll understand how that can be really useful to us. But right now, I just want to assemble a simple circuit. So I want to start by providing 5 volts to my power rail. That way, I can connect anything I want straight to 5 volts, like if there was a battery there. I also need ground, so I'm going to take another wire over to my ground rail. So now if I connect anything between these two rails, it's the same as if I connected them straight to a 5-volt battery. Now I need an LED, so I can place one. And there's a drop-down menu where I could change its color if I wanted to. That could be useful later when we're making our traffic light. But for now, I'll go with red. And again, you'll notice the 2 different terminals, the anode and the cathode. Another way to think about the positive and negative terminals of the LED is to think about alphabetical order. A comes before C in the alphabet, so the anode is the positive terminal, and the cathode is the negative, because current flows from positive to negative. So with that in mind, I want to make sure I connect it correctly in my circuit. So I'm going to place it, and I'm also going to need a resistor. When I place the resistor, you'll see a window will come up that will ask for what resistance I need. I'm going to leave it alone for now, but you can change this number to vary the value and see how that affects your LED lighting up when you build your circuits. Now, I need to start off with something. So I'm going to connect a wire from my positive terminal to this row. This seems like a good row to use. And I'm going to place my resistor in the circuit, following the conventions of the breadboard. I know this is connected to this. So if I place this resistor here, I've connected from this row across to here. Now I have my LED, which I'm going to rotate again, making sure to know that this positive terminal needs to be here. So actually, there we go. I rotate it this way, and this is my positive terminal, this is my negative. My last step is to connect my negative back to my negative terminal here, and my circuit is complete. At this point, I want to see if it works, so I'm going to click Start Simulation. The Arduino was plugged in, and now it's energized, and I can see, yay, my LED lights up perfectly fine. So I have a working circuit. But as one last thing, I just want to demonstrate quickly, what would happen if I forgot the resistor? What would happen to my circuit? So I'm going to delete this, and I'm going to replace it with a wire. Now there's no resistance on the path from my 5-volt line through my LED back to ground. What if I click on Start Simulation now? Uh-oh, I get the little explosion symbol. If I highlight it, it'll actually tell me the current too. I'm only allowed to have 20 milliamps of current in my LED, and I tried to put 483 milliamps through. That was not good. My LED is now burnt out. This is why you have to use resistors, even if it seems counterintuitive at first. Too much current can actually be a bad thing, and we do want to avoid that. With this in mind, I now want to explore a little bit about the coding section before I introduce you to a coding example of a circuit. Okay, we're almost there. This next section will introduce you to the final missing piece of the puzzle, the software. This is how we'll take the Arduino from being basically a glorified battery to a true embedded intelligence. Remember, your mission for the final project is to design this Arduino to function as a traffic light. That's going to take a bit more than just plugging something in once with a few circuits. we're going to have to be systematic about our approach because this is a lot more complex. This is how all software is developed. First, we identify our objective, which we know to be developing a traffic light. Great. Next, we have to consider the constraints or the limitations or rules that we have to follow. In this case, we know that we need our traffic light to repeat over and over because it has to complete that cycle over and over. We need a red light that's going to last this long, a yellow light that lasts this amount of time, green, and so on and so forth. After we have these constraints in mind, we need to develop an outline for what will happen in order, because the computer thinks step by step. This outline is what we call pseudocode. This isn't actual code yet, but we think like a computer when we write it. More on the specifics in a second. Once we understand that flow, we write the actual code, line by line, again, because computers go line by line. We test little pieces of it along the way to make sure there aren't really any big errors or bugs. And then once we get that working, we write a little bit more and we build up an increasingly complex program. Finally, we test the completed program together thoroughly. This is called the debugging phase, especially paying attention to situations where things can go wrong, what we might call failure points. In this case, the test is pretty simple. We're just seeing whether it lights up correctly, it loops correctly, each light is on the right amount of time. But in more complex programs, you can understand why this step is so important. So if you've ever heard of video game debugging, for example, this is what they're doing. They're looking for all the places that the software could go wrong, and they're fixing that before they release it to a consumer. So back to that point I made about pseudocode. When we think about the logic of the program, we want to think like a computer, going one step at a time. We can write this outline, which usually takes the form of a flow chart, where we think through the steps in the decision-making process and consider what needs to be turned on or off, when and where. This example here shows you the thought process of operating an alarm clock. Using our traffic light as another example, when you sit down to write your code, you want to go through the steps the Arduino has to take. For example, we need to start somewhere, right? So let's say red. The red light has to go on and the other two colors have to be off. Then I have to wait some amount of time with the red light on, and when that time is expired, I have to turn the red light off and turn the yellow light on. And then I have to wait and then go on and do the same with green. Then I have to loop back. Thinking through this like the computer will help you tremendously in the process before you even write a line of code. If you try to write code immediately, as a coder, I have had this happen before. You try to write code immediately, it's a disaster. So always give yourself an outline first. It will make your life 1,000 times easier. At this point, I'm going to show you how to make an extension to the circuit we built before in a blinking LED using the code feature in Tinkercad. So looking back at our circuit, we now need to, well, first, I'm going to fix that resistor before I forget because I don't want my LED exploding again. That would make me very sad. But now I need to have a way to turn the LED on and off. So that's not going to be accomplished by just using the 5-volt pin like a battery anymore. Now we bring in those digital pins that I discussed before. So I'm going to get rid of this wire first because this doesn't help me, but I'm going to keep ground. You always want to connect to ground. So leave your ground connections alone. That part of the circuit is exactly the same. What I'm doing now is I'm giving my circuit a new plus terminal in effect, and the digital pins will serve that purpose. I'm going to be using pin 9 because that's what my code is written for, but of course, you can use other pins when you design your circuits. I'm going to connect that to the positive part of my circuit. Now I have my circuit complete. It's otherwise exactly the same. I'm just trying to flash the LED by changing that voltage rapidly. That is where I need code. So if I open my code tab, I'll see this stuff pop up. This is block code. If you're familiar with our robotics maker block lab, you've seen this before. We're not using this today, however. So I'm going to go up to where it says blocks, and I'm going to change it to text, hit continue, and now I have code in C, which is what we're going to be doing our coding in today. If you've done any C coding, this may look a little bit familiar. Before I paste my code in, though, I want to just draw your attention to a few of the things that you're going to see when you use your workbook and go through the minutia of these codes. First of all, we have this thing called setup. This is a function, and inside the setup function, we do things that happen once, the first time that you plug in your Arduino. This is where we do things like setting up the pins modes. The reason we need to do that is because each of these pins could be an input or an output. An output meaning we can use it like we're about to, a voltage that turns on or off, which can make something blink. But it can also be used as an input. If you're connecting a sensor to it, for example, you can actually read the voltage from that sensor, which the Arduino can then manipulate in its code and do some interesting stuff with. It's part of the thinking process of embedded intelligence. We're not doing any of that today, though. We're going to be using it only as an output. But you have to tell the Arduino what way to orient that pin. The other function that we have here is loop. Now, you may have realized that we're going to need to repeat something over and over again. And if I just wrote the lines of code to turn off, on, off, that would be infinite lines of code. That wouldn't be very practical now, would it? In order to get around that, we have this loop function. And what happens is any code that we write inside this loop function, which means between these two brackets, anything here will be done endlessly. So it'll execute this line of code, then this line. Oops, didn't want to do that. Then this line, and then go back to the top, and then do this and that and this and that, end and end, on and on and on until the end of time, or until you close your browser window. This is very useful when we want to do things infinitely, like blinking something endlessly, or perhaps a traffic light. So keep that in mind. This is where you want to do most of the heavy lifting in your code. The last thing I'm going to draw your attention to is these kind of beige looking lines here with the two slashes. These are what we call comments. And what comments are is stuff that the computer doesn't actually execute. They're written there solely for the benefit of us humans. If I'm looking at this code without any comments, it may be hard for me, especially in a complex program, to know what's going on. Especially if I wasn't the author of this code, I might wonder, gee, what did the author mean by this? Why did they write it like this? What's this function supposed to be? It can be hard to interpret. We write little messages to ourselves where we tell us, this function waits for 1,000 milliseconds. This one waits for 1,000 milliseconds. And we can put headers at the top where we tell, this program is supposed to do X, Y, or Z. These are just little ways of you to keep track, kind of like doodling in the margins, but for code. These slashes tell the computer not to execute this as code, which avoids there being any errors. But with that in mind, I am now going to paste in the code that I have written, which is going to make this blink. As you can see, I'm setting an output, I'm turning the LED on, I'm waiting for 1,000 milliseconds, which is 1 second, I'm turning it off, and then I'm waiting for 2 seconds. So if I put that away now and I click Start Simulation, I should have, yay, a functioning blinking circuit, as you can see here. And this is the most basic type of thing you could code. This will be one of the example circuits in your workbook. But I hope that this gave you a little bit of a flavor and a little bit more comfort with what's going on in Tinkercad. At this point, I'm going to give you the final specifications for your traffic light and bring this presentation to a conclusion. So now that you've gotten the hang of the practice circuits, you're ready to design the full-scale traffic light. The exact specifications are as follows. You're going to want to take those sample circuits and build them up to create a circuit with 3 LEDs of the appropriate color, red, yellow, and green, that operates as a traffic light. Specifically, we want the red light to remain for 3 seconds, the yellow light for 1 second, the green light for 3 more. At that point, of course, I want to loop back. I want this traffic light to work endlessly. I may have hinted a little bit about how you can do that. Then I want to think about how you can improve the circuit design in any conceivable ways. Can you change the rate of blinking? Once you have it working like this, please feel free to experiment with changing the length of time that any of the lights are on. The cool thing about Tinkercad is that you can do a lot of experimentation, and we're really excited to see what you guys come through with the labs. So although I just told you exactly what you need to do, and that's what you should start by doing in your student interactive workbook, please feel free to experiment and show us during your wrap-up sessions. Completing this circuit will show your mastery of the skills, but your creativity will really shine beyond that point. This brings us to the conclusion of our main presentation. At this point, you're ready to run off and start working in Tinkercad. Now, we talked about a lot of topics today, so if any of them resonated with you and you'd like to learn more, here are a few examples of the topics that you or your teacher may want to research more. I want to draw your attention particularly to the Internet of Things, because that might be the most familiar sounding to some of you because it's a big buzzword these days. And really, what it is if you took these embedded systems and you put Wi-Fi or Bluetooth in them so that they could start talking to each other over the internet. And if you've ever heard of smart homes and smart thermostats and stuff like that, that's exactly what Internet of Things is. Your thermostat can talk to your refrigerator, can talk to your garage door, and you can control it all on your smartphone. That's Internet of Things. And of course, again, I can't stress this enough, engineering is interdisciplinary. These listed on the side here are just some of the majors and fields that are relevant if this topic really spoke to you. But remember, many engineers work with embedded systems, so this is by no means a comprehensive list. At this point, I'm going to continue with a discussion of our extension activity for this lab. If you're interested in exploring this activity, please keep watching, or feel free to come back to this section after your traffic lights are complete. Otherwise, I wish you good luck with your builds, and thank you again for joining Engineering Tomorrow. We look forward to seeing you in our live sessions. So if you're returning this video at this point, hello again and welcome back to Embedded Systems. For those of you who just came from the last slide, I'm glad you guys are still here too. At this point, we'll be discussing this extension activity that I'm very excited about, where you'll be programming a multicolor LED. Specifically, you'll be able to make this very special LED any color that you want. Along the way, you'll also learn the basics of RGB color, which is how modern computer and TV screens work. So if you're like me, you may think color is really, really cool, and you may also wonder, how can we make any color we want on a TV or computer screen? Or more generally, how do those even work? Well, one of the cool things about color, which you may remember from art class in fact, is that we can combine different colors to create other colors. This leads us to something that we call an RGB LED, which is a special LED that has a red, green, and blue LED inside of it, and can turn any of them on if you apply a voltage to the correct terminal. You'll soon see, using the various combinations of these three, we can create any color we want, just with a little bit of red, a little bit of green, and a little bit of blue. I have a quick video for you now that will help reinforce what I just discussed, and it will also show you what a physical RGB LED looks like in real life.
So we've talked a lot about LEDs and like how does an LED work on a semiconductor level. We've talked about some of the pros and the cons of the LEDs, and we've also talked about how an individual LED can be dimmed, whether through PWM or through analog current control. So we've discussed all of these things before, but now we want to talk about RGB LEDs and how to use them to produce different colors. So an RGB LED is basically an LED package that can produce almost any color. This is great because it can be used in a lot of different applications such as outdoor decoration lighting, stage lighting designs, home decoration lighting, LED display matrices. They're really cool, so you can use them in a lot of different ways. So RGB LED literally stands for red, green, blue, and so the way you get all of these different colors is by making either the red, the green, or the blue brighter or dimmer, however you need to get the exact color you want. In my mind, I think of like when I'm looking over the design guy's shoulders and I see on their screen there's this wheel and it just shows all the rainbow of the color in different areas, and then they just kind of choose what they want from that to get the color they want. You can do the exact same thing with an RGB color. So again, only thing you need to do with this RGB LED is to set the intensity of each leg to combine them together to get the color output that you want. In this case, we're using pulse width modulation to adjust that intensity individually, and the trick here is that our eyes will see that combination of colors instead of the individual colors because the LEDs are very close to each other inside. And when I say the LEDs, that's the funny thing. So an RGB LED is actually simply 3 LEDs that share either common cathode or common anode. So as you can see here, there are 4 leads, and one goes to the red LED, one goes to the green, one goes to the blue, and then in this particular one, it's a common cathode. If you look inside, you can see that the longest lead is actually connected to the base there. It's the biggest piece of the structure inside. So literally an RGB LED is 3 LEDs stuck together in one particular package. And that makes it really easy because then you don't have to put 3 LEDs together and hope that that's good enough, and it makes it a little bit more space saving, and having the common cathode or anode, if you get one of those, is really, really helpful.
So in that video, we saw a color wheel brought up, like you may have used before in design software, perhaps when selecting, say, a font color in Microsoft Word. The neat thing about that is that red, blue, and green are primary colors in design, which is, for the artists out there, a little bit different from painting. But if we shove a red, a blue, and a green light, teeny tiny little guys, in a single package and keep it relatively far away from our eyes, we'll actually be able to create the illusion of other colors. For example, if I combine a bright red and a bright blue light with no green, I'll get magenta. And then if I vary the shades of red and blue a little bit, I'll get the other shades of purple, like violet and lilac and stuff like that. Interestingly, yellow comes from green and red together. If you're a little confused from art class, that's because we're in this case adding color, which is causing the electromagnetic waves to interfere in a slightly different way than what happens when we combine pigments in paint. But this use of tiny lights with different colors is how the pixels on your computer screen operate. So now you can go home and you can tell your parents exactly how that annoying LCD TV screen works and why that little pixel in the corner that never changes color is so annoying, because it's no longer changing RGB. Only one of them is on at any one time, and that's why that one pixel is always red. Now you know why. You also might be curious too, these are all the different colors. How do I get white or black? And the answer is white comes from all of them being on at high at the same time. So full blast RGB, I get white. And because the backgrounds are black, if I turn them all off, I get black. So that is how you get the full spectrum of color. And you can represent images on a little screen or a big screen and control it with an embedded intelligence. You may also recall from the video that he mentioned pulse width modulation that can be used to control the brightness of each LED. If you're coming back after having done the student interactive workbook, you'll recall this is how the analog write function that you use in example 4 operates. For those of you who haven't gone into the workbook yet, this is a function that we use to create a dimmer, where the LED is not fully on, but not fully off. It's sort of a less bright color. Essentially, what this was rapidly turning the digital pin on or off at a frequency determined by the value you put into the function. Using that, you were able to, or are going to be able to, dim that LED. This is the same principle that you want to use in the RGB LED. To get those intermediate colors I mentioned, like those other shades of purple, for example, you need to select the appropriate values for all 3 terminals. There's this amount of red versus this amount of blue versus this amount of green. This leads us to something called hex color code, which tells us exactly which values to use for each of R, G, and B. We've provided a website that allows you to find these values for any color you want, so you don't have to figure them out on your own. There's also some stuff on that website as well, like hue, that we don't have time for, that are interesting to explore. So do know that color does get a little bit more complicated than just R, G, and B values, but these are just the basics that we want you to experiment with and that you can use with your LED. But know that there's a whole breadth of things out there about the nuances of color and brightness out there. For your challenge, we want you to wire up the RGB LED in Tinkercad and code it to produce your favorite color. Feel free to pick any color you want using the website to find the values, and then make the LED light up in that particular color. The circuitry here should be pretty simple, just the Arduino and breadboard with this new LED and a single resistor. Remember, we still want to avoid short circuits. This guy can be shorted out just like the regular LED, so resistors are still important. So most of the work, though, will be in your code. That's the less familiar part. As a hint, though, think back to how we designed the dimmer practice circuit, and think about how this LED is basically 3 LEDs operating. They're just in the same package, but circuit-wise, still 3 separate LEDs. So those are kind of the hints I'm going to give you. Once you get that working, as a final challenge, try to recreate the traffic light using only this LED. That'd be a really cool way to show that you've mastered everything from the main lab and the extension activity. At this point, you're ready to get started. If you haven't already, you can find these slides at the end of your student workbook in the extension section. Feel free to continue exploring Tinkercad, though, even beyond. There are so many different things you can find in the drop-down menu. There's a lot more you can do with the RGB LED. Maybe you can cause the colors to fade in over time. I know a lot of people have those LED strips in their bedrooms that kind of fade from one color to another. Try to create that in Tinkercad. You'd be surprised that the code is not that complicated and combines a lot of the stuff that we've already done in this lab. So I think that'd be a really cool way to extend if you guys just want to really dive deeper into this. The possibilities are basically endless. But this brings us to the conclusion of our embedded systems presentation. Again, I hope you all have fun with your builds, and thank you again for joining Engineering Tomorrow. We look forward to seeing you in our live sessions. Happy building!